actually thought it would be better to have a video going through the answers of the questions that you can find in the download. The reason for that is the concepts are not that tricky. Where you tend to be examined on the idea of Wien's law and the Stefan Boltzmann law is, doing the problems. So I thought I'd just go straight into the problems. You can find these questions in the download section. So question 1A, we are looking to find the luminosity or the total power of the sun. So we're going to use this equation here. And A is the surface area of a sphere, and we assume that stars are spheres for these purposes. And we're given some data. We're given that the radius of the sun is 6.96 times 10 to the 8 meters, and the surface temperature is 5,800 Kelvin. So let's find out what the surface area of this sun is by popping in the numbers. And we'll square that. And that's going to give us a value of 6.087 times 10 to the 18 meters squared. That's our surface area. So let's pop that into our equation here. P equals, this sigma here is the Stefan Boltzmann constant. 5.67 times 10 to the minus 8 times our area, which we worked out a second ago, and times t to the power 4, so 5,800 to the power 4. We'll pop that into our calculator, and our answer will be 3.906 times 10 to the 26, and power is in watts. Now, what is the data given in? That's in 3 significant figures, that's in 2 significant figures. So let's give our answer to 2 significant figures. So it's 3.9 times 10 to the 26 watts. Part B is we are looking at the power emitted per meter squared. So we're going to take the total power and divide through by the area to find per meter squared. So you cancel out. Or you could say, area equals 1 meter squared and pop that in. That's the same thing. So we're going to say sigma times 5,800 to the power 4 divided by the area that we worked out earlier, 6.887. I'm not going to, you can see that I'm using a more accurate version or a more precise version of the area here. I don't want to summarise that down until the very end. So our power per meter squared is equal to just popping the numbers into my calculator. I'm not getting the right answer. Give me a sec. 5.67 times 10 to the minus 8 times 5,800 to the power 4, which is 6.4 times 10 to the 7 watts per meter squared. That's number 1. On to number 2. Number 2. A star emits electromagnetic radiation with a peak wavelength of 6.8 times 10 to the minus 7 meters. When we're talking about wavelengths of light, I actually always convert it to nanometers because I've got a better sense of where they sit inside the electromagnetic spectrum. Okay, and I know that 680 nanometers it's roughly in the red end of the spectrum. That's red light. It's very helpful to know roughly what the wavelengths of each colour of the electromagnetic spectrum is. So A, use Wien's law, or Wien's law in German, I can't say it, sorry. 2.9 times 10 to the minus 3, and t is equal to 2.9 times 10 to the minus 3 divided by 680 times 10 to the minus 9, which is nanometers. and that's going to give us a temperature of 4264.7 Kelvin. Everything has been given to two significant figures, so we're going to round that to two significant figures, so 4,300 Kelvin. That's our surface temperature. Obviously the core of the star will be a lot hotter than that, but the surface temperature is what Wien's law will give us a temperature of. Calculate the power of the radiation emitted by each square meter. So again, we've got power over the area is equal to our power law divided by area. So we're actually looking at the Stefan-Boltzmann constant times temperature to the power 4. So 5.67 times 10 to the minus 8, which is a constant, times, and we won't round just yet, to the power 4, and that's going to give us a value of 1.938 times 10 to the 7 watts per meter squared, and we'll round that down to, I think we can go to 3 significant figures there, couldn't we? Because the constant's given to 3 significant figures, so 1.94 times 10 to the 7 watts per meter squared. That's question 2. Question 3. Two stars have the same luminosity. Okay. Star A has a surface temperature of 5,000 Kelvin and star B has a surface temperature of 10,000 Kelvin. Which is a larger star and by how much? So let's start by creating some equations. Luminosity of A is equal to sigma, the area of A, times the surface temperature of A to the power 4. And we can make a similar equation for the luminosity of B. That's the area of B times the temperature of B, or the surface temperature of B to the power 4. We know that luminosity of A is equal to luminosity of B. So let's equate those equations. Power 4. We can cancel out the constant on both sides, and we can pop in the temperatures. So area of A times the temperature of A, which is 5,000 to the power 4, equals the area of B times the temperature of B, which is 10,000 to the power of 4, which gives us A of A is equal to 16 the area of B. And what I've done there is I have taken that down to there. Okay, and we end up with the area of A is 16 times the area of B. So star A is larger by a factor of 16. That's question 3. Question 4. Describe how the colour of light from a star can be used to determine the surface temperature of a star. So each star, or each colour, sorry, has an associated wavelength. And this is where I was talking about earlier. You should really learn some of the wavelengths of some of the colours. So for example, yellow light has a wavelength of around 580 nanometers. Orange light has a wavelength of around 615 nanometers. Infrared radiation, so if it's, you can't see it in the visible spectrum, but you can see it through an infrared camera, it's got a wavelength of around 700 nanometers. I mean, ultraviolet can be all the way down to 100 nanometers. So having a rough idea of what these wavelengths are associated with colours or parts of the electromagnetic spectrum can be useful. Now, by observing a star and observing the main colour of the star, by observing the main colour or wavelength of a star, you can deduce surface temperature using Wien's law. I'm just not sure I'm pronouncing Wien's law correctly. Please forgive me if I am not saying it correctly. Okay, that's question 4. Are we on question 5? Yep, question 5. So question 5, the diagram below is a sketch graph of the black body radiation spectrum of a certain star. Explain the term black body radiation. Okay, so black body radiation is the radiation from a perfect emitter. Now you may ask, what is a perfect emitter? Well, a perfect emitter is a black body. So, a body that perfectly absorbs and perfectly emits radiation appears to have no reflecting power. It means it doesn't reflect any light. Therefore, a black body is a black body because it doesn't reflect anything. And if we assume something's a black body, the radiation from that body is called black body radiation. B. Copy the graph into your notes and label the x-axis of the graph. Okay, so we've got the graph here. And we've got intensity here. Sometimes described as power density, watts per meter cubed, or intensity. And here on the x-axis, which is the question for C, is surface temperature. And temperature is always given in Kelvin, don't give it in Fahrenheit or degrees Celsius. For C, on your graph, sketch a black body radiation spectrum of the star that has a lower surface temperature. Okay, so we know using Wien's law, so lambda peak times T is equal to a constant. So if we decrease the temperature, then the lambda peak, the peak wavelength, has to increase. So we're going to look for, if that's our peak wavelength of this one, then we're going to have a higher lambda peak. So we're going to have a lambda peak around here for a lower temperature. And our patterns distribution is going to look like that. So C is a C solid red line above. And finally, are we finally? Yep, D. D. The star emits black body radiation that has a maximum intensity at a wavelength of 0.9, so lambda peak is equal to 0.97 nanometers, which is 10 to the minus 6. Deduce that the surface temperature of the star is about 3000 Kelvin. Okay, lambda peak times temperature, surface temperature equals 2.9 times 10 to the minus 3. You can see that from the equation above. So T is equal to 2.9 times 10 to the minus 3 divided by 0.97 times 10 to the minus 6, which gives us an answer of 2989.69. The data in this question is given to two significant figures. So let's round down to two significant figures, and we are at 3000 Kelvin, which was predicted in the question. Prove that it's 3000 Kelvin. So question 5 is complete. Question 6. Data for the surface temperature T and the radius r of two stars are given in the table below. Using only data from the table, determine the ratio of luminosity of A over luminosity of B. Okay, so luminosity of A is equal to sigma 4 pi RA squared times temperature of A squared. That's just using the equation above. And luminosity of B is equal to sigma 4 pi radius of B squared temperature of B to the power 4. We can cancel out these and we'll pop in our data. So 8.7 times 10 to the 11 squared. I keep saying so in a very odd manner. I do apologise about that. I think I've been on my own too long today. 6.8 times 10 to the 7, that's the radius of B, that's correct, times the temperature of B, which is 2 times 10 to the 4, to the power 4. And we pop all the numbers into that, and that comes out with 82855.8. And let's round that to two significant figures, which is 83,000. So the ratio of luminosity of A over luminosity of B is 83,000, or you can write it like this, equals 83,000 times the luminosity of B. Question 7. Got my notes here. Question 7. A star has half our sun's surface temperature and 400 times our sun's luminosity. How many times bigger is the radius of this star compared to the sun? Well, let's call it star X. And we know that the temperature of X is equal to half of the sun's surface temperature. So it's half of the sun's temperature. And we know that the luminosity of X is 400 times the luminosity of the sun. We can, how many times, so we're interested in the radius. So the radius of X squared is equal to the luminosity of X over 4 pi to the power 4. So I've just rearranged the Stefan-Boltzmann law to find out what the luminosity, to put it into in terms of the radius. And I'm going to do the same for the radius of the sun. Radius of the sun squared is equal to the luminosity of the sun divided by 4 pi sigma the temperature of the sun to the power 4. So let's put radius of X squared over radius of the sun squared, and we'll put this up here. So Lx over 4 pi sigma Tx to the power 4, and then we'll put the radius of that in here, which gives us Ls over, but that takes it up, 4 pi sigma Ts to the power 4, and these all cancel. So we're left with a slightly nicer looking sum of Lx Ts to the power 4 over Ls Tx to the power 4. Now instead of putting in Lx, we know that Lx is equal to 400 Ls. And instead of putting in Tx, we know that Tx is equal to 0.5 Ts. So let's substitute them in. Rx squared over Rs squared equals 400 Ls Ts to the power 4, and Ls times Tx to the power 5, so 0.5 Ts to the power 4. Obviously 0.5 is equal to half, and if you do that to the power 4, That is 1 over 2 to the power 4, so it's 1 over 16. So let's substitute that in. 400 ls ts to the power 4 over ls 1 over 16 ts to the power 4. Let's cancel out the ls's, cancel out the ts to the power 4s, and we're left with 400 over 1 over 16, which is equal to 400 times 16, and our answer becomes, let me just put that in the calculator, 400 times 16, which is 6,400. But the question's not finished yet because we've still got those squared values in there, equals 6,400. So let's take a square root of both sides. So that means that Rx over Rs is equal to square root of 6,400, which is 80. So Rx is equal to 80 times Rs. So the radius of this planet X is 80 times bigger than the radius of the Sun, which is what the question asked. Bit of mathematical manipulation there, but it worked out in the end. And we have one question left, question 8. Question 8a. Bellatrix is a star in the constellation of Orion. It has a surface temperature of 22,000 Kelvin. 22,000 Kelvin. Calculate the peak wavelength of Bellatrix. So lambda peak equals 2.9 times 10 to the minus 3 divided by 22,000, which gives us a value of 1.32 times 10 to the minus 7 meters. And again, I like to put that into nanometers because it helps me work out where it is in terms of the electromagnetic spectrum. That is smaller than blue, so I'm suggesting that that's below the violet section, so I think that's ultraviolet light. Question B. Which region of the electromagnetic spectrum does the peak wavelength of Bellatrix fall into? Ultraviolet. So you would really see a strong intensity of light if you were to look at this star through an ultraviolet camera. C. Sketch the black body radiation curve for Bellatrix. Label both axes with a suitable title. So we'll have intensity here, and we'll have surface temperature here. And that's going to be Kelvin, and that's going to be watts per meter squared or per volume. We'll have the classic black body curve, and this peak radiation here is going to be 132. That's not surface temperature. That's going to be peak wavelength. It's going to be wavelength. Oh no, have I done that wrong in the last question? I think back ages ago I gave the wrong answer. Eek. Oh, I'll go back and look in a second. Ugh, how annoying. Okay, D. Bellatrix has a total power output or luminosity of 9.23 times 10 to the 29 watts. Calculate the radius. We want to find out what the radius is. So power equals sigma 4 pi r squared, temperature to the power 4. So 9.23 times 10 to the 29 equals 5.67 times 10 to the minus 8. That's our constant. Times 4 times pi times r squared times 22,000 to the power 4. So we're going to rearrange for r squared, but let's just do this first. 9.23 times 10 to the 29. We can do all these multiples here to make it a bit simpler. 1669 times 10 to 11 r squared. So r squared is equal to 5.3 times 10 to the 18. So r is equal to 2.35 times 10 to the 9 meters, which sounds about right. And 3 significant figures is fine. So there's our answer to D. Now to investigate, let's go back and see where I did some questions on where is it? Where's the question on Wayne's law. Here we are. Was that right? Yeah, the surface temperature. How annoying. That's supposed to be... Is that surface temperature? No, it's supposed to be wavelength. And that's meters. I do apologise. Forgive me. Okay, that's us done. Have a great day.